Greetings 2021ers, this is Professor Kaufman, and what follows will be a survey of what to expect for Project 2, how to get started, and a few tips to speed you along the way. This project's a little bit shorter in run than the first, and most students don't have historically a lot of difficulty with it. But nonetheless, I encourage all of you to get started early, as one of the tools that'll be introduced, the debugger, will prove useful largely as you move ahead in your programming career. The project's divided into two problems. The first involves writing some code, and the second involves making use of the debugger in order to figure something out, which we'll get to in just a second. But let's take those in order. As it was the case for the first project, there'll be a code pack to download along with a make file that automates a bunch of parts of this thing, testing it, so forth. And there's also a manifest of what you can expect to be able to download. That's in there. Let us start with this clock problem and give a brief survey. So some of you may find yourself later on in your career in an embedded programming context. Oftentimes, as you'd work in this, you'd code in C, sometimes in assembly, but most often in C, possibly C++. That's because embedded programming is coding on small devices where memory is very limited, and you have fairly direct access to hardware, oftentimes represented through variables that appear in C. We'll practice this by simulating a small LCD clock. Many of you have seen this kind of thing before, and we'll see some pictures of it in just a second. These are often run by microcontrollers, which are just a small CPU that's meant to run a single program rather than share a bunch of programs with a bunch of users as a full-bore micro, let's say microchip, or let's see, I can't remember. I'll think of it in a second. At any rate, if you've played with Arduinos before, this is very much like it. Not so much on the Raspberry Pi, which actually can run operating systems. Rather, microcontrollers run this single program to fulfill a small duty, such as updating the time as various things come into play. So this simulation then is going to have some code around it. It would be fun to be able to provide devices for this, but we just don't have the resources for it. And one of the things that you'll see then in the C program as we begin to work on it is that it's responsible for extracting some sensor value, which tells you more or less what time of day it is, but then converting that sensor value into an hours, minutes, seconds sort of delineation, and then manipulating another variable that controls part of the hardware that will actually display the time in a human understandable portion. Let's take each of those in turn. They're described briefly here and then in some more detail as we move on. There'll be a so-called time of day register, and we'll talk more about registers later in the class, but it's essentially a hardware location where some value is stored, and it's exposed to your C program through a global variable. It's in all caps, time of day port here. It's typical for global variables to have sort of all caps like this, but not necessary. And it has a slightly weird value. It gives you the number of seconds, or sort of 16ths of a second since the beginning of the day. So ostensibly this would reset every midnight and then start counting up 16 times per second. But this allows you then to calculate a time of day if you know how to manipulate it. So for instance, you take this value and divide it by 16, and that will be the number of seconds since midnight. And then if you further divide it by, 3,600, which is the number of seconds per hour, you'd know an hour. However, that would be like an hour that's like 0 hours since midnight, or 1 hour, or 13 hours since midnight. And you further then have to do a little conversion to get it into a 12-hour format, which is typically what we're going to want. So rather than 0 hours, midnight is expressed in Western cultures as 12. Rather than 1,300 hours, this is expressed as 1 p.m., as it were. So interestingly, you can do parts of those calculations, for instance, the division by 1/16 using bit shifts. And if you mask off the low 4 bits or so that's going to be shifted off, that would be remainder, which allows you to say, oh, if more than 1/8 of a 16th of a second has passed, then I can round my number of seconds up. And then through a series of divisions, dividing by 60 and 3,600 and so forth, then you can calculate hours and minutes and seconds and so forth. Eventually, you'll modify a second clock display port variable that actually controls some output for this stuff. So we'll talk about that presently. This clock display port is just an integer, as was the time of day port. But it's not actually meant to represent a number per se. Instead, each bit of the display port is tied to a little LCD panel that can be lit up or left blank. And this allows, through the arrangement of those LCD panels, to display numbers. So here's some examples. Each of the little configurations is going to have 7 different spots that you can sight up, and for convenience, we'll number those 0 to 6 as what you'd expect in sort of a bit context. So if I wanted to display a 0, then I'd plop down at some part of that display port integer the following bit sequence. This 0th bit is tied to the top panel for the LCDs. The 1th and 2th bit are the upper left and upper right little panels. The 3 is the middle one here, and so on down the line, 4, 5, and 6 on the bottom. So if I wanted to play 0, I just need to leave this 3 blank, turn everything else on, and you can sort of see the shape here of a 0 associated with this. Whereas a 1 would just be the 2th and the 5th bit over here. Now, forgive me, these diagrams are tedious to construct, and so I can't promise I haven't made some errors in here. I'm pretty sure the pictures themselves are correct, but the bit strings that are up here, there may be some bugs in them, so as you find those, report them to me. At any rate, knowing these bit patterns then will allow you to construct somewhat more complex times. And the integer itself that shows time has 32 bits, not all of which are used, that are tied to different parts of this little display. So if I wanted to display the time 8:39 or 8:39 p.m., these little colon dots here were always going to be lit up. However, if I wanted to show the 9 at the rightmost spot, then I take one of those bit patterns up here, this 9, and I'd shuffle it in at the low order 7 bits in this number. If I wanted to show a 3 over here, then I would need to take this bit pattern for 3 and get it scooched over here starting at bit 7. And each of these, then the 7, 8, 9, 10, 11, 12, 13, etc., they follow the same, like earliest one is the top part, last one is the bottom parts with stuff in the middle sort of going left, right order out there. So just plop a 3 down here. If I wanted a 3 here on the rightmost side instead, then I'd shuffle these over here. If I had an 8, 3, 3, then you'd see the same bit pattern here as here, etc. And as I'd want to show a blank, it's all zeros over here. The exception to this is the top 2 bits here, the 28th and the 29th bit, they're going to be attached to a little sort of display that shows an AM or a PM, which can be turned on in full or turned off in full. It being 8:39 p.m., then I'd want to have the 29th bit set because that turns that on, the 28th bit off because this will turn the AM, or leave the AM off, as it were. Another example down over here to show the time 12:05 a.m., which is just after midnight, the following sort of sequence of bits within that 32-bit integer then should be displayed. Now, right away, you should start thinking of this then. It's like, oh, this number, this integer isn't a number at all. It's actually each of the ones here is a true-false that says whether to light some part of this up or not. And the regular pattern associated with these that's emphasized in these diagrams where there's 7 bits here, 7 bits here, 7 bits here, 7 bits here. It's one you can exploit because if you have the bit pattern for 1, then you need to get it over here to the 21st bit to put a 1 at this spot. And that can be done with a left shift. If you then combine that with other patterns to OR them together, then you construct this rather complex display in a fairly programmatic fashion. So there's some mention here then of what those look like and some discussion of those stuff that's down over here that is worth reading. The 3 basic functions that you will need to implement are as follows. A set TOD from sex, this struct, which is listed down here, has a layout of how many seconds has passed since the beginning of the day, and break that then into the number of seconds in the hour, the number of minutes in the hour, and what hour it is, along whether it's AM or PM. The second function is to write a set display from the time of day, this TOD struct here. So this will modify this display integer based on the contents of this TOD struct. Is it 12:05 p.m. in 16 seconds? Then put that in here. Construct a little bit pattern in this display akin to what's up here to show that it's 12:05 a.m. And then finally, a sort of wrapper function around these, a clock update, which calls the other 2 functions in order to facilitate time changes. This would be done continuously then at regular intervals by the hardware that be on this little clock simulator. These 3 functions are the only required code that you have to write, and they should be in a file called clockupdate.c. I think that's mentioned here. Yeah, clockupdate.c. This isn't provided. Instead, that is one that we'll have to create. So I think we may as well get started on the coding portion of this now. As usual, I'm going to grab the code pack here. I'm just going to copy the link address rather than downloading it so I can put it right to where my shell goes. So I'll use a wget for that. So that downloads it. So in addition to some old stuff, I have this p2code.zip, and I'll unzip that thing and change into the p2 code directory. And if I open that up over here, you have things like clock.h and clock main, which would be the main routine, clock sim, which is supporting routines, some examples of stuff, and then stuff associated with testing and the second problem we'll get to later. But there is no clock update .c, so I will create one here, whatever you need to do to make a new file. In my case, I type an esoteric keystroke and do clock update.c. Down here, which will create a new file that looks like this. It's very likely that I will need stuff from this header in it because I'm going to be modifying these structs and want to abide by the calling conventions that are laid out in the header for these things. So let me first and foremost pound include that clock.h as it were over there, so I have access to those things. I may want to do some debug printing at some point, so I'll also include the sdio.h in there. And then I'll need these three functions. It'd be handy to have the documentation provided in the spec associated with them, so I'm just going to buzz over here, come over to this thing, and start copying here. So I'll grab this thing and plump it down here. And then over here, grab this set display from int there. And then down here, take out the documentation associated with this thing, clock update. Cool. Okay, so those stubs then, I can fill in a little bit better. Let's see, let's take this thing and I'll just move it down below the comments. Here, it just needs to return, 1 maybe. That's a good start. And since that'll probably be something I'm doing several times over, we'll plop that down to move this up here, and then take you, move you down here, and grab the return one. Cool. Okay, so that's all I need to do to sort of get this dummy definitions for these functions up and running. If I jump over to my shell, I should be able to make prob1 right now. Let's see, undefined reference to set TOD from ports. Did I have... Oh, shoot, I have the wrong name in the spec, so I will have to go change that from ports rather than sex. That's what happens when you change your mind too many times. Only pause to do that just so that folks following on at home don't get confused by that. All right, with that minor correction, now we've got a compilable and runnable thing. One of the things that you can do is actually run the clock main over here. Clock main. And this will require an argument, or it'll take the current time of day on the Unix system that you're at. In this case, it's 2:53 p.m., and so that would be a sensor value of 857,520. Clock main up here, I can also just pass a 0 to it to say it's midnight. You can see not much is happening here. Eventually, this will display some digits, and we'll look at some examples of that in a second. For instance, one way to affect this right away is to say in the second function over here, this is a variable is a thing. If I set it to be some bit pattern, that's what gets reflected over here. So for instance, I set it to be display equals 1, which just has a single bit in it. And I recompiled and reran. Let's see. Well, that's interesting. I would have expected there to be... Oh, it errored out, damn it. That's right. Okay, so I'm going to actually return zeros for these instead so this thing actually runs. I'll make it a little better. And then here, Nope, still no good. Oh, rats. Okay. Well, let me pause so I can figure out. Well, maybe if I. Um, hmm. Oh, it's going to be uninitialized, and so this is going to go. No, it should be. This should be working now. Okay, this is going to bug me in a second. What if I did -1 instead? I don't suppose that's going to. No. Okay, let me pause and figure out why this is going sideways. Okay, I'm just being an idiot here. We don't need it up here in this one. But down here, need to set the global variable clock display port over here to be something. So here, clock display port equals 1. I was, yeah, just being a moron there. And as I'd run this now, hey, there it is. There's this little bar over here. That's the top bar of something. I can get them all to light up if I set this thing to be -1. So I'll make that again and rerun, and you can see, oh, there's like 8, 8, 8, 8, 8. And that's on account of, you see the 8 a.m., AM and PM over here. If you look back at these diagrams, handily linked here, the diagram of time display, all ones over here is going to turn on everything in their cousin. So in that respect, this stuff will... it's certainly not a useful pattern, but you can see you can affect the display in that respect. So then, with that in mind, the main sort of objectives here then are to start wheedling away at this and filling in sensible definitions. The test cases should run at this point, so you'd make test prob 1, and these things, of course, will all fail right now. Each of the tests then have a little a fixation over here, which indicates which of the functions they relate to. I think I have a couple of omissions there, but all the set functions, those deal with this first set display from ports business over there. And you can see here, if I look at the test failure, that all it's really doing is saying set the time of A to be 0, so it's midnight, and then print out what values are associated with each of these. It should be midnight here. I'm also probably going to get some Valgrind errors because my function currently does nothing to the time of day struct that's passed in, and that means each of these things are going to be uninitialized, and Valgrind tends to have beef with that. So to start out with, I might do something really simple that would cause me to pass this first test but not be able to pass anything else. Here would be, let me say TOD hours equals 12, and TOD, let's see, I can't remember the field name, so let me go to the header quick. It's day sex here, day sex equals, let's put it at 0 for now. And then here we'll have hours, we'll have minutes. Actually, it's time sex though. Time hours, time minutes, time sex. These should be zeros probably. And we'll have the AM, PM equal to 1. That's going to get the very first test case rate, I think, but not otherwise pass anything else. But it's just to show some progress there. Let's see, time, I think it's mins instead. So I wanted to be slightly shorter there. There we are. See, A-OK. Oh, and I even got the next one up right too. Now, this is not the right way to go about it. And instead, I'm going to want to grab this global variable that's up here, time of day port, and do some stuff with it to calculate if I divided by 16 and then did proper rounding here, then I would be able to get my time of day sex, and then start dividing this one by various things to get the minutes, hours, seconds, and so forth over there. Keep in mind the constraints that are mentioned over here, and these are in place for a couple different reasons. First, you'll want to do the time of day with the number of seconds calculated from this port using bit shifts. That's part of the grading criteria. And you'll use a logical sort of mask off the last 4 bits, because that'd be the remainder there, in order to calculate. If it's 8/16 of a second or more, then you should round it up. Otherwise, leave it as is and truncate it. The other constraints are to favor integer operations here. Probably unless you do something a little weird like cast to a float, that's going to be default anyway. But a lot of these embedded microcontrollers don't even have a floating point unit on them. And so the need to do floating point operations is, well, I mean, if you needed to, then you'd have to emulate it in software. We don't in this case, that everything can be done with integer operations. Floating point units are complex, and so they're somewhat expensive. And while your desktop computer and your phone certainly have one, really cheap dollar microcontrollers that are in embedded devices like clocks, they don't need that kind of stuff. So why bear the expense? Pass it on to the consumer or the stockholders, as it were. The other constraint is that this function, when you finish it, should be pretty short and concise. I would expect no longer than 40 lines. Try to avoid as much as possible doubly and triply nesting conditions. While it's tempting, at some point in the future, we are going to convert all of this code to assembly. The shorter and cleaner your code can be in C, the easier time it will be to convert this to assembly. Now, for the second function, you'll want to make use of various bit shifting patterns here. And this will be to say, okay, as I look at my hours, I have a 1 and a 2 in it. And I'll need to extract that from the hours in some way. Extract, similarly, the 2 digits that will be in the minutes. There'll be some special cases, like we don't see 01 p.m. It's just 1 p.m. But if it's 9:06, the 0 actually should appear there for the minutes. But essentially, lay out several variables that are associated with the digits as they should display. Then it's extremely useful to have a little table that says at the 0th entry here, the bit string for 0 is present. There's some description of that in the specification. Let's see, I think it's down over... Now here, I guess there's a simulation answers that we'll look at over here. Here, the description and hints about how to do this. So you create an array that has at least 10 entries in it for the digits 0 to 9, and you can plop down then these binary constants in there that you derive from the diagrams of like, oh, if I want to display a 0, I'll put this bit string for 0 in the 0 spot. I mean, this isn't it. I think this one is actually. And if I want to display a 1, then I put that in the 1 spot. That allows you to say, oh, if my minutes digit is 5, then go into this table, this array. At the 5th index is the bit string to put at the spot where I should put minutes. Shift that over by some amount and OR it on to the complete sort of integer, and you'll be well on your way to sort of constructing that entirety. The only thing that remains then is mentioned out here to shift a bit over to either the 28th or the 29th position based on whether the AM or PM should be set. After that sort of finishes up, the clock display thing is really easy. Like you maybe need a little stack variable, and this is here then to get you practiced at calling functions that you've written from other functions that you've written. Probably most of you are in good shape. There are a whole bunch of examples in here that you can obtain once your clock simulation is sort of running okay. Of, for instance, command line value 72,115. This equates to 1:15 p.m., 4,507 seconds since the beginning of the hour, 3,600 seconds per hour, so you can sort of do some head calculations there. But it should bring it to 1:15 and 7 seconds there. Just be mindful that some of these actually have some rounding, and some of them are embedded in the test cases that are associated with this. So yeah, I think that should be sufficient for the moment to get us going. The grading criteria that are mentioned here, we should be abide by, and the only one that sort of bears special mention is shortness for particularly the first and second functions. You'll want to make sure that you try to have concise code, and then make use of shifting operations where it's mentioned. You will have to do some division because figuring out is in this decimal number of 37, like to fish out the 3 and the 7, dividing by 10 is like basically the easiest way to do it. Okay, let's move on to the second problem, which is entirely different in nature. I've provided code for you in the form of a program called Puzzlebox. Let's have a quick look at it. It's in the code pack here, puzzlebox.c. Has a bunch of sort of setup in it, but basically the main function, it starts out here, prints some stuff out, runs this function, and if you return from that function, you earn some points. Runs this next function, returns from that, you earn some more points, and so forth. The functions themselves are going to require some inputs that you provide in order to actually finish. And if the inputs are wrong, this function will never return. It will cause the program to exit out. One of the things that will be interesting about this is that the input file that you provide has to start with your X500, like my old student X500, COF0095, all of you have one, and that will seed a random number generation to some extent. That'll make your answers ever so slightly different from your neighbor's answers for this. So let's see how this thing sort of works in practice. Grab my shell back up again. I think if I make puzzle boxes are here, so here's puzzle box. I need an input file for this. There's a sample input file provided here, sample input.txt. Let me make a copy of that. So copy sample inputs to the required input.txt, which is where your graders will look, and then run puzzlebox on it. Input.txt. That's there, and I should probably change my X500 here. So if I pull up that input.txt, I'll change this to COF0095. So running on this thing, I have COF0095 accepted. It gives me a hash value, and it's like I did not pass through here. Well, that's kind of expected because it's the default answers, and why would it provide default answers that actually work for folks? Although I can't guarantee maybe some of it will work because it's randomized. If we looked back at the Puzzlebox source code here, we'd skip down to phase 1 here, which is not passing. And if I find it beyond all the setup functions, it's here. You'll find that this next input is going to draw something out of that input file, and in this case call the A2I function on it. If you weren't aware, it'll convert character data, the A part, to integer data, and assign it in this case to A, and do so 3 times for A, B, C there. To that end, the numbers here have to satisfy a certain relationship. A is less than B, B is greater than C, A is less than C, save for the fact that A is going to get modified by hash mod 41 here. Now, you can see on the shell here that my hash value gets computed out, and one way to do this then would be to manually find a calculator that could handle a number this big, and then compute mod 41 on it to get some number in that range, and then you'd have a sort of fighting chance. But this is missing the point to some extent of the exercise, which is instead to make use of the debugger to solve this much more easily. Allow me to demonstrate, for which I'll get an actual shell up here. Because the debugger that will use GDB has a few sort of niceties that are in play when you use an actual shell versus my Emacs subshell here. To start the debugger, I'm going to fire up GDB. It takes a program as an argument, so puzzlebox here. And then we'll do some other things for the second, but first I'm just going to fire that up. You can see over here then I get a little command prompt, which is the debugger in action. Traditionally, this is how you'd interact with a command line debugger, but it has a sort of clunkiness to it, which we can alleviate by using a text interface. There are 2 ways to do that. First, I'll quit. You can start this on the command line by saying -2e, text user interface. And after paging through just a little bit, you'll see, oh, this actually shows a source code up here with my little command prompt down here. And we'll see how to do that elsewhere. If you happen to have started GDB without enabling that 2e, you can turn it on and off by doing a 2e disable if you wanted to turn it off for some reason, or 2e enable. That'll turn it back on. Now, debuggers are powerful time control tools that allow you to stop at any spot in your program and sort of inspect values to see what's happening there. So you'd want to stop at a particular spot. You'd set what's known as a breakpoint. And the easiest way to specify a breakpoint is to break at a particular function. In this case, we could break at phase 01, for instance. Now, GDB is aware that there is a phase 01, and so I set a breakpoint at a particular memory address for a program instruction. The only thing that remains is to let GDB know that there's a command line argument to this. So I'll set args here to inputs.txt. At this stage, I punch run. I may have to get a prompt or something like that, but the screen's getting a little bit garbled up here. The text user interface that we have is it gets messed up as things get actually printed, like the normal GDB stuff. This isn't a problem in the normal command line prompt, but it's not a problem here either because you just jam the keystroke Control L, and this will refresh the screen. And you can see time has stopped right at the beginning of this phase 01. And I can now proceed to take steps through the program by, for instance, using the next command, which will move to the next line of C code here. And then print out what is the value of A. Now, well, it's 1. So I buzz back over here to my inputs.txt. I can see that's the first number I entered, so that sort of makes sense. If I next again, I can print B. That's 2, and that's again C. Let's see. Oh, here. I forgot next, so I printed out the random value that's presently in C, so I'll call next now. And then print out C, it's been overwritten to be 3 instead. If I step one more time, I can then I can see what has A transformed to. It was 1, and now it is 36, because apparently my hash mod 41 is 36. Now this should make it relatively straightforward to figure out, okay, I need A to be smaller than B, so I can make B 37 or 38, 39. B has to be bigger than C, and C also has to be bigger than that. So I'm going to fish around for some values, like A, if I leave it as 1, it's going to become 36. B, I'll make 40, and C, I'll make 37, because I think here A has to be smaller than it. And now that I have new input values in here, I can rerun from the beginning of the program. And as I would next here, if I print now, here's A, and notice the shortcut kind of just say PA, PB, and PC. I think that will satisfy this set of conditions. So as I punch next, I'll move forwards. I'm about to return, which is good, because if I didn't return, I'd hit this failure business down here, which is no good. Next out, finishing up the function, and now I've got myself some points. With that new input, you could also run this on the command line to say, here's puzzlebox input.txt, and you can see that phase 1 is a pass, and so I've earned myself 8 points total. There's warnings on here that there are no more inputs which would be used for the next phase, and so I'll probably want to plop some things down that seem relevant to the next phase by looking ahead there. We may as well sort of move forwards here, so I'll next over this print. I'm about to get to this phase 2. There's one other command that allows you to move forwards. It is step, and this is short for stepping into a function, whereas next will pass over functions. So in this case, I'm in phase 2. I need 3 more integers, so maybe I'll just take over here the input.txt, the 1, 2, 3 again. And I maybe take a pot shot here. If I run it again, nope, I did not get the second phase to pass, so still at 8 points. And I'll want them to be non-blank, so I'll rerun from the beginning. Irritatingly, I still have a breakpoint here in phase 1. Let's get rid of that. If I wanted information on all my breakpoints, it's typed info break, and this would list the only one there. I'm going to want to start stopping at phase 02 here. And so now if I do an info break again, I've got 2 breakpoints. including I've already hit this one. And I don't really want to stop at that first one anymore, so I'm going to delete it. So here's delete one. And so now info break. And at this stage, I don't feel like rerunning, so I will continue, which is just keep going, executing code until I hit the next breakpoint, and here I'm in phase 2. So your basic cycle is going to be to trace through the execution of code here, to try to predict values, try them out, and then use the debugger to sort of step through and see what's happening there. You can see there's some interesting programming techniques that are used here in the puzzle box, as it were, that you'll maybe need to reacquaint yourself with, but no matter on that account. So your basic cycle, like take a crack at a phase, use the debugger to step through it. Once you get it done, then add some new inputs for the next phase. You can see over in the specification the scoring that's associated with these, along with some tips of useful functions that are in there. Let's see, where's that scoring at? Did I leave it out? Okay. So each of the phases has like a different sort of amount associated with it. We can actually see it in the source code for this. If I look at puzzlebox.c, the first, second, third, fourth phases are 8 points apiece, and then progressively somewhat smaller after that. There are 60 total points available, as mentioned over here. But you only need 50 to get full credit for this, as the last few stages are a little bit harder. But if you get all 60, then this will earn you some makeup credits, which, for instance, if you lost some credit on Project 1, then this will backpatch that and sort of fill into your project totals. So it won't allow you to exceed 100% on the projects, but it is useful if you think you might lose some credit later or already have done so, then that can help to mitigate those effects. There'll likely be some makeup credit available elsewhere as well. There already was on Project 1. So yeah, I think that's about it. So this should be enough to get started in terms of the first few phases. Next week's lab on Wednesday will feature some discussion further about using GDB and surveying it if you need some additional help there. As usual, make sure to make tests to check both Puzzlebox, which will just run the Puzzlebox with your input.txt, and the first program, which will run the automated tests associated with it, before submitting your code to Gradescope. And there's no grand manual inspection criteria for Puzzlebox. It's just passing phases and learning what the value of GDB is. That's all I've got for now. Good luck to all of you, and I'll see you in lecture. Happy hacking.